Now let's talk about asymptotic normality and hypothesis testing. Asymptotic normality and hypothesis testing is what that should say. Testing. Sorry about that. Hopefully it's all on the screen. Hypothesis testing. Hypo testing, let's say. All right, so if you remember in that last module we did hypothesis testing, we made 5 assumptions previously in the module before, and then we added this other one, right? So we made last module, spelling's rough today. Last module made assumptions 1 to 5 that we've talked about a number of times now. So linear and parameters, IID. We need some variation in X, so we needed no perfect multicollinearity. That 4th one was the expectation of U given all the X's equals 0. Remember that 5th one was about homoscedastic errors. So the variance of U doesn't depend on the level of X. And that 5th one we made, so that was that 5th one, was the homoscedastic. And we made this assumption about normality. Plus, we made this assumption that the U is distributed normal. So this was that normality assumption we made. So we made that assumption. That's how we derived the distributions of our estimators as well as the test statistics, right? So we kind of talked about how last time, once we made that assumption, if we took our estimate, subtracted, the true value, or what our hypothesis of the true value is, I guess, and if we divide it by the standard error, standard deviation, we'd get a normal distribution with a mean of 0 and a variance of 1, because we're subtracting the true mean. We're dividing by the standard deviation. And then we talked about how if instead, because we didn't know the population variance, so we had to estimate the standard deviations, we estimated that through the standard error. We figured out that this was a t distribution with n minus k minus 1 degrees of freedom. And so remember, this was the distribution of our t statistic, because essentially we're taking our estimate, subtracting what our hypothesized mean of that, like the true value of that parameter is. I mean, that's what we were testing against. And we're dividing by that standard error. So let's talk a bit about what this assumption we were making actually was saying. It was this assumption about the U is about the assumption about the Y's as well. So what does U distributed normally 0 sigma squared imply about the distribution of Y? Well, that it's also normal. Also normal. So this assumption we're making about the U's is implying that all the Y's we've been looking at are normally distributed. But in a lot of the cases we've been looking at, a lot of the variables and situations we've been looking at it, there's no reason to think that those Y's should be normally distributed. So let's kind of take a closer look at this assumption and kind of think about if we let n go into infinity, maybe we can use the central limit theorem to help us out. So remember, this normality assumption tells us nothing about unbiasedness or anything like that. We were just using it for hypothesis testing. So remember this assumption about the normality of the error term of U, let's just say, had nothing to do, had no influence on unbiasedness, had no influence on unbiasedness, but we use it for hypothesis testing. So if y's aren't normally distributed, then we need to use the central limit theorem as n goes to infinity to be able to know how our OLS estimators are asymptotically distributed. So if y is not, or all the yi's, maybe is a better way to put it, normally distributed, we need to use the central limit theorem, CLT, to conclude that our OLS estimators are asymptotically normal. Asymptotically normal. So we made this assumption about the u's were normally distributed. And this implied that the y's were normally distributed. So remember, this had nothing to do with unbiasedness, had to do with hypothesis testing, understand the distribution of our estimators. So if the y is not normally distributed, if that assumption is too strong, we're going to need to use the central limit theorem to be able to understand or conclude that our OLS estimators are asymptotically normally distributed. So where the central limit theorem was, we talked about in the review of stats that the mean of any random variable is distributed normally as n goes to infinity. So now, if we make the assumption as that n is going to infinity, then for each j, just like before, we had beta hat j minus beta j over the standard deviation of beta hat j. That's asymptotically normally distributed with a mean of 0 and a variance of 1. That's just like before, but this little a means asymptotically. And now, if we use the central limit theorem, then even when we use the standard error, because we don't know the variance of the population, we use the standard error instead, this is also going to have an asymptotically normally, it's going to be asymptotically normally distributed with a mean of 0 and a variance of 1. So what this means is when we're doing hypothesis tests, let's say on a single parameter and a single restriction, just those simple t-tests, we can, if the sample is large enough, we can start using critical values and things like that from the normal distribution. We wouldn't be doing exact tests there, but they'd be asymptotically valid, and asymptotic is going to work, with any kind of decent sample size. Though kind of modern day computers will just calculate these exact tests automatically. And let's also just talk about the variance for 1 second. The variance of beta hat j, the estimated variance. So it's just the same formula. I'm just going to put SSTJ there. Remember, that's the variation of x, or it's kind of n times the variation of x, which we'll talk about in 1 second. And then 1 minus r squared j. Remember that r squared j was the r squared from regression, the xj with all the other x's on the right-hand side as independent variables. So let's talk about these different components as n goes to infinity. Well, that pen's not working very well. Let's try a different color. So let's say that's 1. We'll say that's 2, and that's 3, and we can talk about them over here a bit. So 1, as n goes to infinity, sigma hat squared is going to be a consistent estimator of sigma squared. So it's going to go to its true value as n goes to infinity. It's going to be a consistent estimator. The second thing is r squared j, which is kind of, it's kind of capturing this correlation between the x's, or xj and the other x's, I should say. But it's an r squared, right? So it's, as n goes to infinity, it's got to go to some number between 0 and 1. Because r squared has to be between 0 and 1. So even as n goes to infinity, there just must be some correlation between this xj and these other ones. And the third one, so let's remember, SSTJ was equal to the sum of x1, I guess I'll say xj, minus x bar j squared. Well, that equals n times the variance of xj. Just by if we multiply this, I mean, maybe the way to see this is the variance of xj equals 1 over n of the sum of all these things. I'll put that in brackets. And so this SSTJ is n times the variance of xj. So 1 over n times SSTJ equals the variance of xj. And so SSTJ is going to be approximately equal to n times the variance of xj. And so what's happening here as well is that as the sample size, this is shrinking. The variance is shrinking by a rate of 1 over n, as the sample size increases, right? So this is why a bigger sample is kind of better. All right. So now if we're thinking about using asymptotics, we can think about using just the normal critical values for these simple t-tests, because now under our null hypothesis, our t-stat is going to have a normal distribution. It's going to be asymptotically normal with a mean of 0 and a variance of 1. Our estimated variance, so this is the formula for the estimated variance. We're talking about what happens as n goes to infinity here. Sigma hat squared is going to be a consistent estimator of sigma squared. This r squared j is going to equal some number. As n goes to infinity, it's got to equal some number between 0 and 1. And this SSJ is kind of calculating, it's kind of related to this variance of xj. Okay, so that's kind of what this module was all about. It's really technical. We didn't really get into a lot of the details of what's covered in your text. But I try to cover the most important parts of this chapter.